Good afternoon, everybody. I'm Lilia Boeri from La Sapienza, and I'm talking from La Sapienza in Rome. And before I say anything scientific, I really want to thank Thomas and Elio for inviting me. I would have really loved to be in Busnau, as I've been in Busnau for many years. I was starting to miss it, but unfortunately, this is not possible. So I hope there will be other occasions in the future. And okay, so today I will talk about ab-initio designs of new conventional superconductors. I'm sorry there are not so many correlations in my talk, but I hope it will still be interesting for you. And so let me start with the first slide. So I think you have seen these plots many times on any talk about superconductivity. So this is the plot that shows more or less the increase of TC as a function of year. It starts in 1904. And the nice thing of this plot, I think, is that it ends at 2020. So actually, the things I want to talk to you about are things which are happening in this region. So these are news of the last 5 or 6 years, let's say. So here in this plot, we see the usual thing. So we see that for the first 70 years of superconductivity or so, there is a very slow increase of TC as a function of year. There is, I mean, if one computes the slope, there is an increase of 0.3 Kelvin per year, which is very low, until one hits a maximum of 25 Kelvin. And there were, I mean, for a long time, this maximum was not increased, I mean, was not overcome. So there were even smart people who actually formulated an explanation of why this maximum exists. So there is the famous Cohen-Anderson limit. And the Cohen-Anderson limit is based on BCS theory, or better on Migdal-Ellsberg theory, and says that more or less there is a maximum of 25 Kelvin and it's not possible to go beyond. So as you all probably know, there is the first thing that breaks this limit is in 1986, the discovery of high TC cuprates. And you see here the slope is much higher. I mean, TC goes up very fast, and it goes up to 156 Kelvin. And I think the only thing that people more or less agree about is that, I mean, there is, let's say, no predictive formula. There is no quantitative explanation that can tell us why TCs are so high. But the only thing that I think everybody agrees about is that these compounds are not conventional, so that conventional superconductivity doesn't apply. So somehow this also the high TC cuprates don't break the Cohen-Anderson limit. So I would say that the first time that really, the first discovery that really challenged this idea that there is a maximum TC of a few tenths Kelvin for conventional superconductor is this discovery in 2014. So it's this point here. You see there is a TC of over 200 Kelvin, 203 Kelvin in SH3. SH3 is a hydride, so it's a high pressure hydride. And you see now there are actually a lot of these red dots on this plot, and they all contain hydrogen. And if you read here, I mean, all the pressure are very high. So these are high pressure hydride in the sense that you need hundreds of GPa, which means millions of atmosphere to produce this compound. Anyway, if we now compute the, let's say, the slope of these discoveries, I mean, not only we have a lot of discoveries in less than 6 years, but we even have a regular increase of TC. So we have a TC which goes up by 12 Kelvin per year. So it's a factor 40 faster than what we had before. And the question that really one can ask, I mean, there is this is called in the field, this is called a hydride rush, because there is a rush to discovering new hydrides. This is now becoming a really competitive field. But the question that one has to ask is the hydride rush completely random? I mean, did it happen by chance, or is there a good reason why at some point, I mean, this field exploded and we found all these compounds? And what I want to convince you about, I mean, what I want to tell you about is that, of course, this is not a random discovery. This is a discovery which was, so how did this happen? I mean, this was made possible actually by the development of and the application, the maturity of methods for ab-initio high TC conventional superconductivity. So let's say there is a completely new way to think about superconductivity. I mean, superconductivity is not just a problem of interpreting the experiment, but it's really a problem of how to design materials, of how to design compounds which have actually high TC. So in this case, which have a higher and higher TC. And what I will show at the end of my talk is that now we are actually looking at ways to design compounds where these pressures, I mean, which actually don't need this super high pressure. Before I do this, I just want to tell you a little bit about these methods which make this discovery possible. So how did this happen? So how can you design conventional superconductors? So the first thing you need something to predict the chemistry of your material. So you must be able, we have all these hydrates which form at very high pressure. You can imagine that, I mean, in principle, one could just go and measure a lot of hydrates, but to do these experiments at hundreds of GPAs, I mean, they're extremely expensive, they're extremely delicate. So you need, I mean, to know where to go and look for materials. So you need a method to predict which compounds would form at a given pressure. And this is a field, so the field in general is called the field of ab-initio crystal structure prediction. And more or less, I mean, there are two things that one has to do. So the first thing is to imagine that you are at a given pressure with a given chemical composition. And if this pressure is very high, I mean, usually the structure that will form has little relation to the low pressure structure. So you need a way to predict the crystal structure. And what you have to do is basically to imagine that you have a really large phase space. So you have what is called a potential energy surface. And the minima, the local or the global minima of this potential energy surface represent structure which are either the ground state of the system at some pressure, or they are a metastable, long-lived metastable phase. So in principle, if you have a chemical composition, you want to find all your local and global minima. So you need to explore this huge hypersurface. And obviously you cannot do this by hand. So you cannot just go and sample all the possible structure. You need some smart way to do this. And there are now many methods which have been developed to solve this problem. I mean, there are evolutionary algorithms, particle swarm techniques, etc. I mean, some of these methods were even pioneered in Stuttgart in the Janssen group. So once basically one finds the stable composition, you need, so you know that a given chemical formula will have that structure, but then when you are in a lab, it's possible that this particular chemical formula is unstable, so that this product will decompose into different subproducts. And to actually predict whether your thing will decompose into these subproducts, you need what is called a convex hull construction, which basically connects, or which basically compares the energy of the enthalpy of all the different phases and find the minima. So this is here, for example, a very complicated convex hull. It's a projection of a quaternary convex hull. So you have boron, nitrogen, oxygen, and hydrogen, and you try to predict the stable compositions. So this is the first part. Then you have, of course, a physical problem. So you know that the structure will form, and then you want to be able to tell whether that structure in particular will be a superconductor. You want to predict the TC, you want to predict the gap, and so on. So for this, you need basically methods. You need accurate methods for the calculation of TC. And also this field has boomed in the last 15 years. And there are now basically two main theories for conventional superconductors, at least. So there is something which is called superconducting density functional theory, which is mainly developed by the group of Hardy-Gross. And then there is something which is called Ab-initio Migdal-Eliashberg theory, which is basically a combination of DFT with more standard Migdal-Eliashberg theory. And now basically the two approaches have a very similar accuracy. So here, this is a plot. This is a nice paper from the group of Hardy-Gross, which actually compares TCs and gap values for basically predicted ab initio and measured by experiments. So these are black are experiment, green are predictions. And you see that for most of these materials, which is, a quite representative set of known conventional superconductors, you have an accuracy of predicted TCs and gaps of the order of 5 to 10%. So basically the idea is that once you have a structure, you can actually say whether this structure is a superconductor or not. Then we have the last question to actually address. We have seen that we have this explosion, we have this hydride rush. So for some reason, at some point, somebody decided that hydrides or hydrogen-rich solids were good places to look for high TC superconductivity. And the idea, the physical intuition is actually quite simple. It goes back to an old idea. So here you can use actually a very simple formula. So we use here the Macmillan-Allen-Dines formula that tells you if you have a conventional superconductor, the critical temperature is basically proportional to the phonon energy scale, and then depends exponentially on a constant, which is the electron phonon coupling constant. And this electron phonon coupling constant itself has two ingredients. One ingredient is how many electrons you have at the Fermi level, so how many electrons can couple to phonons. And the second, let's say that I would say the most important ingredient that you need to look at is this I, so this constant here, which tells you whether, which is the electron phonon matrix element, which tells you whether in a given compound, the states at the Fermi level couple more or less strongly to the phonons. And now after like a little bit of experience, we know that basically to optimize this I, you need to be in a system where at the Fermi level you have stiff bonds. And so the typical class of system in which you observe this high lambda are so-called metallic covalent solids, which are extremely rare at ambient pressure, but actually the hydrides are a wonderful example of this class of compounds. So let's see this idea of hydrogen-rich solids. So it goes back to Ashcroft. It goes back to a very old idea of Ashcroft. We see more than 50 years old. The first idea of Ashcroft is that actually metallic hydrogen itself could be a high temperature superconductor. Very simple. We look at this formula here. If you have metallic hydrogen, you have, of course, a large prefactor because you have high phonon frequencies. You have large N0 because this metallic hydrogen is a good metal. And you have a large electron phonon matrix element because this hydrogen potentially is very, very weakly screened. So the idea of Ashcroft goes back to 1968. And at that time, it was a sort of dream because nobody had ever metallized hydrogen. And not even nowadays, everybody agrees that this hydrogen metallization has been observed. But if it has been observed, it requires pressures close to 500 GPa, which are at the limit of what one can actually measure in diamond analytical set. So Ashcroft had the second idea, which is this paper from 2004, which is actually the paper which basically started the whole field of high pressure hydrides. And the idea was that if you want to have metallic hydrogen, you don't need to really press hydrogen. So you could do something else. So you can take a solid which is rich in hydrogen and press that solid. The idea is that at some point, the hydrogen atom which are in this solid will form a sort of metallic network. And then the other atoms that you have in this metallic alloys, so the host atoms that you have there, will not bind to hydrogen anymore, but will just act as spacers, and they will basically exert some kind of pressure on this metallic hydrogen network. So in the end, what you will have is what is called chemical pressure. So you will have an effective pressure coming from the outside, which is given by the diamond anvil cell, plus an internal pressure coming from the hydrogen. And in the end, this will reduce the pressure that you need to stabilize a metallic hydrogen lattice. And this is actually the idea that worked. And here you see so this is a periodic table that shows all the binary hydrates which are high-TC superconductors. So first of all, I mean, you can read here, so these numbers here are the TC, and this plot has also another information, which is the hydrogen content. So first of all, we see that all these solids have a very, very large hydrogen content. They have a hydrogen content which is much higher than the hydrogen content that the normal binary hydride would have at ambient pressure. This because basically you normally the way you do this experimentally is to put this thing with the hydrogen gas and the method sucks it in. So and then you see that there are basically two regions of stability and two regions in which you find high TC superconductor. One region on the right part of the periodic table, and this corresponds to so-called covalent hydrides, like for example this first hydride SH3. And then you have another class of compounds with a very large hydrogen content, which are so-called clatrate hydrides. This is just an aside. So these are binary hydrides. Now people are moving to study ternary hydrides, which look even more promising in the sense that, I mean, this is the first, so the first compound where actually real, so here it's missing, but it's 287. So where really room temperature superconductivity has been observed is a ternary hydride. And then you see that there are even higher prediction here, one from Yang-Li group, and even some, let's say, very optimistic experiments which report even 550 K in a ternary hydride. So this is one of the directions in which the field is moving.
Lilia, you have roughly 4 minutes left for speaking.
Okay. So basically here, these are these two classes of high pressure hydrides. There are these covalent hydrides, SH3, that I've shown here. And there are these other compounds. And all I wanted to say is that these other compounds are these soda-like clatrate hydrides. So if you look at the structures, you have this very, you have a perfect realization of this idea of Ashcroft. So you have this very dense, you have these hydrogen cages. In the middle, you have these large balls. And if we look at actually at the lattice, you see that this hydrogen forms a sort of very, very strongly interconnected network, and then these atoms that you have in between push on the network. And what is bad about, what is good about these compounds is that the critical temperature are extremely high. What is bad is that there is a critical pressure at which these solids typically break down, and they break down when the cage becomes too large to enclose the central atom. So something that we have an idea to do was to see whether we could optimize these problems, or whether we could solve the problem that the cages break down. The idea was actually to look at ternary hydrides. So we identified, in particular, we were looking at this lanthanum boron hydrogen system, and we came up with a very nice compound in which you have lanthanum, hydrogen again, and then you have in the middle, in the holes of this structure, you have this boron. And the strange thing is that this boron, instead of bonding to hydrogen, really acts just like a spacer. So, what is nice about this structure is that if you look, it has an electronic structure. I have no time to go into details, but you have basically an electronic structure which is dominated by the hydrogen sublattice. You have an extremely high TC, so you have a TC of 120 Kelvin. But if you read here, this TC is now achieved at 50 GPa, so at the pressure which is 5 times lower than what you need to stabilize lanthanum H10. And if you look, I said before that this lanthanum H10 has a structural instability, also this lanthanum H8 has a similar structural instability. But now the pressure is reduced. The pressure at which this instability occurs is reduced to 35 Kelvin. So we have, by combining basically a typical binary hydride with a smaller atom, we have found a way to reduce the stabilization pressure that you need to observe this, this high TC superconductivity close to room pressure. And what I just wanted to say one more thing is that this is a very general idea. So this is the first example that we found, but there are actually many more compounds that realize this concept. And some have stabilization pressure which are even smaller than 35 GPa. So this is really a way to push this physics down to lower pressure. And I don't think I have so much time. So I just want to recall this idea. And besides hydrides, we are actually applying the same methods. We are looking at different systems. So we are doing a lot of work also on boron carbon system. In this case, we are really looking at the zero pressure phase diagram. So with this, I think I close, and I just want to thank all the people who work with me on this. I mean, my group is a bit still scattered between Rome and Graz, and I want to thank everybody who has contributed to this work and you for listening to my talk. Thank you.